You are on to Mass Secrets Revealed by Dr. OJ. In this video, we shall discuss pointwise convergence of sequence of functions. This is an interesting aspect of real analysis 2 or 3, as the case might be. We're going to talk about convergence of sequence of functions in a pointwise manner. Now, how do we define pointwise convergence? Let's look at that. Let f n as n move from 1 to infinity be a sequence of functions. What do we mean by this? It means that every element in this sequence is a function. It's like saying that we have f1, f2, and so on to infinity. So let them be a sequence of functions and not ordinary functions. Let's say a sequence of real value functions. Let's put it there like that. Let's define it clearly. Sequence of real valued functions. Okay? Sequence of real valued function. Now, it implies that this sequence has functions as its element, like I said. Now, the sequence Fn, converges pointwise to a function f of x if for a fixed x in D, that is the domain of the function, that is domain of the function, Fn. We have the limits as n tends to infinity of Fn of x is equal to f of x. So our limits here is f of x. That is the limit function there is, what are we saying here? We are saying that, let me quickly take us down the memory lane. What this statement first means that is this. Suppose we have this as the domain and we have this. So now we have this is a sequence of real value functions. Okay, a sequence of real value functions. This is the domain of the function. So we fix an element x. Suppose we pick x in the domain. Don't forget, the domain of a function contains x input value, the input values of the functions. It's a function. It's a set of x values in a real value function. So if I pick any element x in this domain, suppose my x is fixed, then I'll be having what fn of x will be a real number as I have it here. So what we are now saying is that if a function is picked, if a point is picked in that domain, okay, now the limit of that real sequence of functions, with respect to a point x in the domain would be equal to a function f of x. That means that if all the functions there, f1, f2, f until to infinity, now is related to a point x in the domain, the result of their convergence, will always be f of x. In this particular type of convergence, we always consider the convergence separately because the convergence depends on x. The convergence depends on the value of x. So that implies that we might get different values for convergence depending on the value of x that is given. Depending on the value of x. This is different from uniform convergence where the convergence does not depend on x, but this one depends on x. So you could have the convergent point for when x is equals to x1, when x equals to x2, you could have something like that. Let's illustrate with an example. Let's illustrate this with an example. Let's illustrate with the example. The example will give us more understanding of what we are talking about by the pointwise convergence of sequence of functions. Pointwise convergence of sequence of functions. Now, let's look at this example. Let's example. Let fn of x be equals to xn on the interval 0, 1 for each x in that interval. Now we have, okay, let's look at the so we want to show that show that the convergence is pointwise. The convergence is pointwise. We want to show that the convergence is pointwise. Okay. Now, one, we claim to show. We claim to show that when x is in the interval 0, 1, consider this half closed interval. That is when x is 0. That's what I mean by that. When x is 0, let's check. When x is 0, you know we said that recall for pointwise convergence, the limit as n tends to infinity over fn of x will be equals to f of x. And this invariably means the absolute value of fn of x minus f of x will tend to 0. Okay? So it implies that our x per n now tends to 0 because our fn of x is what? Is xn. So are we together now? Fine. Beautiful. And if we say that x is in the half closed interval, it means x is 0. So you can even show from here, you can say xn minus x raised by 0 raised by n. Obviously, it means that xn, the absolute value of xn tends to 0, obviously. That's what I mean. Okay? Because my fn of x is x raised by n. So x raised by n minus f of x now, our f of x now, because our x is 0, so that is what? That will be what? 0 raised by n. And 0 raised by n is 0. So absolute value of xn minus 0 is xn. And it tends to 0. Okay? Now you see that when x is equals to 0, the value of our convergence it tends to 0. You can see, I think this is a subset of this. This is, you can see that it's only talking about 0. What? 0. Okay? 1 is not included. Now let's now look at when x. So now with second condition is when x is equals to 1. So by the time your x is equals to 1, then xn will be equals to 1 raised by n. And that is going to be what? That is going to be 1. Okay? So that's going to be 1. So that implies that when x is equals to 1, it's what? It points, its point of convergence is equals to 1. So which invariably means that this particular function, fn of x is equals to xn, converges pointwisely. It converges pointwisely. So now we can now write it as a limiting function. Therefore, the limiting function. Let me write it up. Let me rewrite it. Therefore, the limiting function f of x now. Therefore, the limiting function f of x now. The limiting function f of x therefore the limiting function f of x will be is equal to You know it's 0 when 0 is less than or equals to x less than 1. And it's 1 when x is equals to 1. So it implies, you could see that x is the one that determines the point of convergence of this function. When x is 0, you see that it converges to 0. When x equals to 1, it converges to 1. So on this note, we have come to the end of this particular video. So please do well to click on notification bell so that by the time I produce next video, you'll be daily notified. God bless you.